Welcome to this lecture series in group theory. In the previous lecture, we looked at an example which was supposed to motivate the notion of a group. And now we want to give a formal definition. And to do that, first we will discuss the notion of a binary operation. And then in the next lecture, based on this concept, we will give a formal definition of a group. All right, so let's get started. So what is a binary operation? Fix a non-empty set S. A binary operation on S is a function from S cross S to S. No, that's it. It's a function from S cross S to S. So that's a binary operation. It's a very abstract and a very general definition. Unclear why this is useful, unclear at all as to what does it have to do with symmetries. A group is supposed to be the symmetries of some object, and the notion of a binary operation has been given to build to a definition of a group. So all of that is unclear, but that's okay. We will, in this lecture, treat it as a very abstract definition, and to understand or get a feel for an abstract concept, what you should do, what anyone should do is to look at a lot of examples, and we will do that. But before we do that, let me mention that this terminology is very appropriately chosen because binary means something to do with 2, right? And what is this function doing? It is consuming 2 things from S. Those 2 things are coming in an order because this is the set of all the ordered pairs of elements of S. So this function is consuming 2 things in S and again and outputting something again in S. Okay, so that's the definition of a binary operation. Let me also put down a notation here. Suppose star is a binary operation on a set S. So typically binary operations are denoted by star. So this here I could just write a star. That's the name of the function that this is. Okay. So if star is your binary operation on S, the value or the output that star gives on this input should be written this way. You should make an extra bracket because this ordered pair itself is an input and that is what you're feeding to the function. So an extra bracket should have been made, but it's a common practice to not do that because it starts looking very ugly. So we write this thing as A star B. Right, so it is just a change of notation, as you must have seen when we discussed linear algebra, but forget about that. So this notation is perhaps good for computers, but for humans this is much better. But it's the same thing. All right, so now let us look at examples. So this is perhaps the most ancient or most familiar binary operation. It's the addition of 2 natural numbers. So this function does what? If you feed it a pair of natural numbers a comma b, it just outputs their sum. This is your usual sum of natural numbers. So let me not say anything about it. Let me just say that it outputs 5 on this particular input. And I'll leave it at that because I cannot explain the addition of natural numbers by breaking it down to simpler components or anything because I can't even explain why 2 plus 2 is 4. Okay. This is another very familiar binary operation which is about multiplying natural numbers. It takes a pair of natural numbers and outputs its product. Let me not waste time by getting into any philosophy here. It's just that it will output 6 on 2 comma 3. That should explain. Now let me define a binary operation on Z. So how are we going to define it? We are defining it as A star B is A plus B minus 1. It's a binary operation. It takes a pair of integers as input and gives this thing as the output. In fact, let me make it more exotic. I'll put a square here. Why not? That's a perfectly fine binary operation. Completely useless maybe, but it's a binary operation. Okay. So suppose A is any set. In fact, I would like to use X. Suppose X is any non-empty set. Then we will define, in fact, we have already seen many binary operations here. One binary operation that we know is union. right? So if you take two subsets of X, then you can produce another subset of X by taking the union of the two things. We are also familiar with intersection. You can intersect the two things from A, and we are also familiar with symmetric difference. So at least 3 binary operations on the power set of X are familiar to us. Okay. This is also very interesting. Suppose X is any non-empty set and S is the set of all the maps from X to X, right? So all the functions from X to X that has been collected in a set, notated like this. So here is one very nice, very familiar binary operation on S is composition, which I would denote by circle. This is small circle. So what does this binary operation do? It takes a pair of functions from X to X and outputs their composite. Right? F is a function from X to X, G is a function from X to X, so we can certainly compose them. And the composite function will also be a function from X to X. So this is a bona fide binary operation on the set of all the functions from X to X. Very nice. And one more example. This is the last example. Suppose F is any field and n is any positive integer. Let S be the set of all the n cross n matrices over the field F. Right? Then we can define this binary operation, which is matrix multiplication. So if A and B are two matrices, n cross n matrices over the field F, we can multiply them. And this is how we write their product. So this is also a binary operation. This product is again going to be an n cross n matrix over F, right? So it's a very ubiquitous concept. It's just that we never look at it in this way, but it is everywhere. Union, intersection, symmetric difference, composition, matrix multiplication, even the usual addition and multiplication, all of these are binary operations. So it's a ubiquitous concept in mathematics. All right, so let's proceed. Commutativity. So fix a non-empty set S, and suppose star is a binary operation on S. Then we say that star is commutative if A star B equals B star A for all A and B in S. In the computer notation, this would be written as star of A comma B equals star of B comma A for all A and B in S. That's just an alternate way of expressing it. So this is called commutation. The order in which the entries are present is irrelevant. That is what it says. We will look at examples, but before we look at examples, let me express this exact same thing by means of a commutative diagram. So suppose I apply star to an element of S cross S. Okay, rewind that. What I'm saying is we have this function star on S cross S or from S cross S going into S. This is our binary operation. Now I will express the commutativity property via the following diagrammatic way. So I have this new map. This is a map from S cross S to S cross S. What is this map? This is the switch map. I'll call it S, or let me not call it S, let me call it psi. This is the switch map. What does it do? It takes A comma B to B comma A. Right? It's a bona fide map from S cross S to S cross S. What does commutativity say? It says that if I apply star here, it doesn't make a difference. Either I go this way or I go that way, the output will be the same. You start with A comma B, you feed it to star, you get something which we denote as A star B. Or you first apply the switch map, you get B comma A, and then you apply a star, you get B star A, and it lands to the same thing. We express that by saying that this diagram commutes. This diagram commutes. So this word commutes is reappearing this commutes and that commutes have nothing to do with each other. It's an unfortunate clash of terminology. This commutativity means you can flip the entries. Diagram commutes means the traffic, or what should I say, the path that you take from your source to your destination is relevant. You will always reach the same output. Okay, so if you saw my linear algebra lectures, you should have already appreciated the power of diagrammatic thinking, this kind of thinking. And as far as possible, I will express things or certainly give this alternate perspective as far as possible throughout this course. Okay, enough of that. So let's look at examples. So this is a commutative binary operation. Addition of natural numbers is commutative because it doesn't matter whether you add 2 and 3 or 3 and 2. Right? So that's clear. Multiplication is also commutative. 2 times 3 is 3 times 2. And now we have this binary operation, which let me define like this. We have to define it. So what is this? This takes a star b to a plus b minus 1. This is also commutative, right? Trivially. And all the operations that we saw about sets, union, intersection, and symmetric difference, they are commutative. So commutative binary operations are also present in good number, but there are important non-examples. The first non-example would be composition. Composition of functions is not commutative. This is certainly not a commutative binary operation, but yeah, I haven't even written the binary operation. So it's the composition. This is not commutative. And I encourage you to figure out an example if you are not comfortable with this statement. It's a very simple set theoretic statement. Easy to come up with a counterexample. Okay, also matrix multiplication is not commutative. You can easily find 2 n cross n matrices A and B such that A times B is not B times A. Clearly this will not happen if n is 1, so you have to take n at least 2. So let me not write the proper statement here. All I'm saying is that matrix multiplication is not commutative and you can justify it for yourself. Okay, so now let's proceed. Associativity. This is a very desirable property of any binary operation. So what does it say? Fix a non-empty set S, fix a binary operation star on it. We say star is associative. If the following equality holds for each A, B, and C. Since you're familiar with linear algebra, all of this must not feel like too foreign a thing. But in the computer notation, what this says is, first you compute the output of star on A, B, and then that output is further fed to star along with the entry C. This is virtually unreadable for a human, while this is very, very familiar. Okay, so we say star is associative if this happens for all A, B, and C. So I should also write that. Okay, a very desirable property, as we will see. In fact, you must already appreciate it. But before we look at examples, let me express this exact same thing by means of a commutative diagram. So this time we take this particular Cartesian product S cross S cross S and map it to S cross S. So what is this horizontal map? It takes, let me write it this way, it is star cross identity. What does that mean? Star is a map from S cross S to S. Identity is a map from S to S. And you are just taking the Cartesian product of these two maps. So A, B, C, I think we need a longer arrow. A, B, C will be mapped to star of A, B comma C. That's what I meant. So when I wrote that, I'm just parsing that. Although if you know your set theory, you already knew what that meant. So what is happening is we have applied star to the first two entries to produce a baby, and the third entry we preserved. And now you can apply star to this guy. If you apply star here, what you get is A star B star C. Well, what I mean is, if you start with A comma B comma C, this way what you will end up at is this guy. So this is just the map star. We know what that is. Okay, now we could do another thing. We could keep the first entry fixed and apply star to the other two entries. So what does this map do? It takes A comma B comma C to A comma star of B comma C, right? And now you can apply a star here. This statement is exactly saying that this diagram commutes. Do not run away if this diagram seems too complicated. It is not complicated. We are just trying to express this equation in a diagrammatic fashion. All of these things are just explanations. If I delete that, it will look better. Okay, so that's that. And now let us look at examples. The usual addition on natural numbers is associative. It doesn't matter in which order you add, whether you compute this thing out or you compute that thing out. It's the exact same thing. Similarly, multiplication of natural numbers has the same property. 2 times 3 times 5 is 2 times 3 times 5. Here, let me not give an example here. You can come up with your own examples, or what you could do is just take multiplication on integers. That is also associative. This guy, what did I do? Union, intersection, and symmetric difference are associative. Union and intersection are associative is a triviality, and we saw that the associativity of the symmetric difference is something of a headache if you approach it purely set theoretically. But if you interpret it as something happening on f2 to the power a, then it's much simpler. So a is your set. I wanted to write an x, but I have written an a. So we saw that in the previous module, that symmetric difference becomes addition on f2 to the power a, where it's very simple to see the associativity of the symmetric difference. Okay, so these are associative, and now composition of functions is also associative, right? So if we take composition as our binary operation, this is associative, right? Just prove it if you are uncomfortable, but I'm sure you've seen this, or you knew this without knowing that you knew this. And do we have more examples? Oh, we have matrix multiplication. Matrix multiplication is also associative. Right? Very easy to, not very easy, but it's easy if you look at it from the linear algebra point of view, because matrix multiplication corresponds to composition of the corresponding linear endomorphisms. And the associativity of composition of linear endomorphisms is just a consequence of this guy. So using that, you can very easily show that matrix multiplication is associative, but directly doing it just by following the bland definition of matrix multiplication, it's a headache. You can do it, you can write things down, but it's a headache. Anyway, but since you know linear algebra, you knew this. And for a non-example, just consider this function. This is a binary operation which is commutative. Clearly, this is commutative, but it is not associative. To see the non-associativity, you can consider this thing. Maybe I'll just consider even numbers for my own peace of mind. So what is this? This value is 4 star 12, because what does this do? It just outputs the average of the two things. The average of these two things is 12, and the average of these two things is 8. But what about this guy? This is equal to 6 star 16. The average of 4 and 8 is 6, and now the average of 6 and 16 is 11. So certainly not equal. So non-associative binary operations also exist, but typically I shouldn't even say typically. I don't know a single example of a non-associative binary operation which is useful. Right? So any binary operation that you will study will be associative. I think so. So this is a very desirable property. Commutativity can be dropped because there are important examples where commutativity doesn't happen. Right? So commutativity we should be able to, or should be willing to relinquish. But associativity, no. There is no single good example where associativity doesn't hold. This is not a good example in some sense. All right. So with that, I want to end this lecture. As usual, like, comment, share, subscribe, and I will see you next time.